Fluxgate Magnetometer, a device to measure magnetic fields. Let's start with a simple coil of wire. When we pass a current through the coil, it creates a magnetic field around the coil. When we stop, the current in the magnetic field goes away quickly. Not instantaneously, but quickly. As the magnetic field collapses, it will create a current flow inside the coil, which will in turn create a magnetic field, which will add to the collapsing magnetic field to make it collapse slower. Okay, so let's insert an iron rod into the coil and pass a current through the coil again. A magnetic field is created, but this time this field is much stronger. The reason this is the case is because of the following. Every piece of iron, including our iron rod, contains lots of microscopic regions called magnetic domains. Each individual domain acts as a tiny magnet, but all of these magnets are not pointing in the same direction. They point in random directions, and the net effect is that they cancel each other out, so the rod is not magnetic, or at the very least doesn't act like one. However, when our coil creates the magnetic field around the rod, it causes some of these magnetic domains to start aligning with our magnetic field. As our magnetic field gets stronger, more domains start aligning with it. As these domains start aligning in the same direction as our field, their combined magnetic field stops canceling each other out, but instead they start reinforcing each other, and a strong magnetic field starts to emerge from the iron rod. The stronger the field, the faster additional domains align with it. Then, at some point, most of the domains become aligned to the external magnetic field. At this point, the iron is considered to be magnetic saturation. That is, making the field from our coil stronger, the external magnetic field will not increase the internal field of the rod by much because most of the magnetic domains in the rod are already aligned to the external field. Let's stop the current flow through the coil once again. We'll notice that it takes longer for the magnetic field to dissipate. This is because of the time it takes for the magnetic domains in the rod to align in random direction again after the external field from the coil disappears. And as long as the majority of these domains are aligned, they have a combined strong magnetic field, which will help slow the dissipation of the total combined fields of the rod and the coil. So far, so good. Now let's get to the part where we actually start detecting a magnetic field. Okay, we understand how the coil and the iron rod, or more properly, iron core, creates a strong magnetic field when we pass current through the coil. We'll extend the core and place another coil next to our first coil. The first coil is called the drive coil because it's the source of the magnetic field that everything else is based on, as we'll see shortly. The second coil we've just added is called the sense coil because this is the coil that will be detecting the unknown magnetic field. When we energize our drive coil, it rapidly creates a magnetic field. As this or any magnetic field grows or shrinks, it will induce a voltage inside nearby wires. In this case, it will be our sense coil. But once the field stops growing, it will stop inducing a voltage in our sense coil and we can no longer detect it. So obviously, the usefulness of our magnetometer so far is severely limited. We can have continuous detection if we keep turning on and off the magnetic field of the coil by constantly turning on and off the voltage in the coil. Our sense coil detects the changing field continuously, which is what we want. But clearly, our magnetometer is still limited because we are not in control of the unknown field to be changing its direction continuously. But this alternating magnetic field allows us to do something interesting. Let's make one minor change before continuing. Instead of going from 0 to positive and back to 0 again, our voltage on the coil now goes from negative voltage to 0 to positive voltage, then to 0, and then negative voltage again. This in effect creates a magnetic field in one direction and then reverses the direction. It's the same square wave but centered on 0 volts. When a voltage goes positive, after a certain time, the core is magnetically saturated as all of the domains align. Then, a little later, the voltage goes to 0 and then in the negative. The external magnetic field will go to 0 and then be reversed. As this happens, the domain becomes unaligned and then aligned in the opposite direction until it becomes saturated again in that direction. This will also take some time. Still, after a while, the voltage will go positive and then the whole process will repeat. The time the core spends in saturation will be the same for the positive and the negative half of the cycle. However, if there's an external magnetic field, not counting the one from the drive coil, it will cause the core to go into saturation faster if it's pointing in the same direction as our field in the drive coil. If it's pointing in the exact opposite direction, then it will cause the core to go slower into saturation. And this time difference is the key to how the Fluxgate Magnetometer detects magnetic fields. After we pass the output of our sense coil through an amplifier and low-pass filter, we will now notice a signal that is twice the frequency of our drive signal. This is called the second harmonic. The amplitude of this signal is proportional to the strength of the magnetic field being measured.